Okay, so let's start our class today. We were in the middle of an exercise. I'm going to quickly redo the parts that we performed last time, and then we're just missing one part, which is to find the constant of integration, but we have enough info to get. So, well, we are given the slope, which is 3x squared plus 1. By this point, okay, we know that the function is obtained by integration, and we also have this info, which is that the function passes through the point 2, 6. So first we have to perform the integration that we did last time. So this would be the integral of the slope function, which is the integral of 3x squared plus 1 dx, which is easy to integrate. Then you have x cubed, plus x plus a constant. So at this point, the integral is indefinite, but you probably know the technique by now, which is that to determine the constant of integration, what you have to use is all the info that you're given. And you know that the function must pass through this point. So basically, by imposing this constraint of the function f at 2 equal to 6, you will find the constant of integration. So again, as a methodology on how to find the constant of integration, so you have to remember that the graph of f passes through the point 2, 6. So for x equal to 2, what you know is that f of 2 is equal to 6, and therefore if you substitute in the function that you have obtained so far by integration, 6 is equal to f of 2, which is 2 cubed plus 2 plus c. So you have 8 plus 2 plus c. And using this, you find the constant of integration, where you have that the constant is 6 minus 10, which is equal to minus 4. And so the final form of the function that we were looking for is x cubed plus x minus 4. The moral of the story is that the points the function must pass through will give you the constant of integration. In fact, when we do another problem, which is related to a physics problem, in a way the initial conditions, which is, say, the velocity at the initial time, or either a given position at the initial time, will give you the constant of integration and will determine the function completely. So you have to get it from the info you're given in the problem, and you can interpret it later on in some physics problem as initial conditions. So this would be the result of the exercise, and this is summarizing the last thing we did before we went to the other class. Oh, well, look, I know my boundary in order to write. Do people need more time, or have you finished copying? So don't forget it. If you're given this condition, passing through a point, that will most probably determine the constant of integration. You need some interpretation in terms of physics problems for that. And we will see a couple last problems, one of them related to business, the other related to physics, and then we jump to the new section. So in the new example, you have 5.1.5. So you have to find the total cost from the marginal cost. And we have done a marginal cost problem before. So look, I have to summarize the information that I present in terms of the statement of the problem. So when you have the marginal cost of a product, that is a piece of information that we were given. So we already know that the marginal, this is by definition in a way. If you want to remember, like 2 weeks ago with a problem, we know that the marginal is related to a derivative, where Q is the units that have been produced, and C is the cost. So the piece of information in the problem is that you're given this function, which is 3q squared minus 60q plus 400, and that is dollars per unit. Remember that you're having a derivative. And the quantity Q is, well, this happens when Q units have been produced. So C is the cost, Q is the number of units that have been produced, and I'm given the function for the marginal cost, which is the derivative of the cost function that I want to find. So clearly the problem is asking me to find the cost function, which will be done by integration. So some of the questions that are asked is basically, well, we're also given again a piece of information, which is passing through a point, kind of, but in this context is, we know that the total cost of producing the first 2 units is $900. Okay? So that is in the context of the previous problem when we know the function passes through a point. And the question is, what is the total cost of producing the first 2 units, of producing the first 5 units. Yeah, that other information we were given for. So we already know for 2 units is 900, what is for 5 units? So since we were given this marginal function, which is dc over dq, what we want to find is first the function c as a function of q, and then c evaluated at 5, which is the question. So, stating the solution, the marginal cost is the derivative of the total cost function c of q, which is what we want to find. We want to find c of q. So this is obtained by integration. So this goes to the material that we did before. If I integrate the derivative of c with respect to q, I will get c of q, and then I will have to determine the constant of integration by means of the information that I have been given. So that is what we will do, and we were provided this function, right? So that is the integral of 3q squared minus 60q plus 400 integrated over the variable q. So you have the dq. So let's do the integration. You have q to the cubed minus 60, then you have q squared over 2, then you have plus 400 q, and then you have a constant of integration, which we will denote by k, because if you notice, the cost function is denoted by c, so we want to avoid some confusion. So here we can do a simplification, actually, which is q to the cubed power minus 30q squared plus 400q plus k. Again, so we will determine the constant k by the point that we were given. Remember the piece of information, right? Basically, we know that, and we see it on the page, yeah. For producing 2 units, the cost is $900. So the point is actually 900. If the x-axis, which is a q-axis, denotes the units produced, and the y-axis, which would be the c-axis, denotes the amount of money, which is the total cost, which is 900. So we already know that 900 is the cost function associated to the point 2. And then we only have to plug in for this function that we have already found by integration to determine k. So that is 2 cubed minus 30, 2 squared plus 400 times 2 plus k. So this is the way we will determine k. So let me substitute. I have 8 minus 30 times 4, 120. Then I have plus 800. And then I have k. So that means that I can simplify a little bit. And then if I pass the numbers to the other side, I have k equal to 900 minus 800 plus 120 minus 8. If you do the actual computation, you get 212. And that would mean that the function that you would have is basically just plugging in the value of k that you have here. So q to the cubed minus 30, q squared plus 400, q plus 212. So at that point, we have the general function. It's only the matter of evaluating in order to get the final answer, which is what is the total cost of producing the first 5 units. So that is C of 5. So if I simply substitute C of 5, I have 5 cubed minus 30, 5 squared, plus 400 times 5, plus 212. And if you do the computation, you get in the amount of dollars, 1,587. But it's just a computation. The key part in the problem, this one is more applied, right? The other was more theoretical, like more pure mathy. In this one, the important thing to do is to deduce from the information that you're given what you have to do. So you were given the marginal so that you know that it's a derivative of the cost function. So that's one piece of information. The other piece of info is that you're given the price or the total cost associated to producing some units. So that will act as the point from which you will deduce the constant k, because by performing the integration of this marginal function, which is a derivative, you obtain the indefinite integral. But the indefinite integral needs a constant of integration to be completely defined, which is what we did when we realized that we passed to the point to 900, which is the cost for producing 2 units is 900. Then we simplify and we obtain k. And in that case, for producing the first 5 units, we only need to evaluate the cost function at 5 units, so the cost at 5, which is this result. So there is an internal logic into how you perform these problems, right? You analyze the information that you're given, you realize what you have to do, which is in this case integrating, then you determine the function up to a constant of integration, and then from the information, extra information that you're given, you determine completely the problem. Done. That is the technique. Okay? This is in a more applied context, the other was in a more pure mathematician context. We will do one last, is there a question actually, or is the procedure clear at this point? Yes, it's clear? So we will do one last example, which, look, I'll give you 1 minute more to copy, but then I will make some background in order to present them. If you think about, okay, look, Newton came up with the calculus, right? And it is because, okay, he was a physicist, he studied many problems, how the apple falls from the tree, whatever. But, well, thinking as a physicist, you want to define the concept of what is velocity, right? And if you basically go through the high school algebra before introducing the concept of calculus, you will not be able to do so because you need a limit process, which is to define the velocity, you basically need this limit as the difference in time goes to 0. So my point is that calculus was born from the physical intuition of these concepts of velocity and acceleration. And that's why it makes a lot of sense to do, even in a business-oriented calculus course, a problem like this to deduce how the information is used. Because what we will have in a physics problem are usually info of the kind of initial conditions, etc. And that is exactly the role of this point to 900 in a business problem that in a physics problem will be perhaps the initial velocity or the initial condition. So now that we can move to the next one, I will give the information associated to the physics problem. Okay? So you have a classical physics problem where you're requested to find the position, which will be denoted by S at the time t, where you define a quantity known as the velocity, which will be the derivative of this position with respect to time. And then you need another concept, which is the acceleration, which is the derivative with respect to time of the velocity. So, this is just some high school concept, or say Physics 101 concept. The example that we will do, which is 5.1.6, it is related to the motion of a car, where the car has a velocity, and then it has a constant acceleration, and that's why its velocity, well, its speed actually decreases until it stops. So the initial velocity, you start from 45 miles per hour, which, if you do the conversion, is 66 feet per second. And then that is the velocity that you start from. And you go to a lower velocity by a constant deceleration of 22 feet per second squared. So if you remember from your, who has seen this kind of problem in physics in high school before? Some people. Yeah, so this is the typical problem you have, right? It's a constant acceleration, naturally the acceleration, which will influence the sign that you put for the acceleration. And of course the units, I mean, because the acceleration is a second derivative, that's why you have the second squared. And the final question is, how far does the car travel before stopping completely? So, the method of solution is in this fashion. You define, of course, the quantity, which is S of t, which is the distance traveled by the car in t seconds, so you're defining the units after the brakes are applied. And you know that the acceleration is constant, but it's negative because you are having a deceleration of minus 22 feet per second squared. So the minus is related to the deceleration. Now, you start to use the physics definitions that we presented at the beginning. So the derivative of the velocity with respect to time is acceleration, which is minus 22, which means that if I want to find the velocity, again, now you see why these physics people invented these math concepts, because in order to get the velocity, you have to integrate the acceleration, which is the derivative of the velocity with respect to time. So that means, okay, I will have to plug in my formula for the acceleration, which is minus 22 and then dt, so use this value, and then I have minus 22t plus a constant c1. Now, there's a reason for the notation, and this is something that perhaps basically we will have to integrate twice, because if you remember, the velocity was the first derivative of the position with respect to time, and the acceleration is the derivative of the velocity, which means that it is the second derivative of the position with respect to time. So, in a way, this probably involves second derivatives, and in order to go from the acceleration to velocity to position, you have to integrate twice. So the first constant we find is C1, because then we will have to do a second integration, which will be C2, okay? It also has its internal logic. You integrate once, you go from acceleration to velocity. You integrate twice, you go from velocity to position. That is the deal. So you also have to use, and now I can say without problem, the initial conditions, because at the initial time, t equal to 0, the initial velocity was 66 in the units of feet per second. That is a piece of information that we were given, okay? And this is just by using the conversion. So, if we do this, we just plug in the formula that we have. So 66 is equal to b of 0, which would mean, well, if I can substitute, if you want, minus 22 times 0 plus c1, which is equal to c1. So now I determined that c1 is equal to 66. Okay? I just plugged in the information of the initial condition regarding the velocity that I have. This term vanishes, so I have c1. So now I can write, actually, the formula for the velocity as a function of time, which is minus 22 times t plus the constant of integration, which is in this case 66. Okay? Because of the choice of units that we have made, etc., etc. So, is the approach of the problem, at least up to the velocity, clear? How we do it? Yeah, right? I mean, it's kind of intuitive, right? Look, this is, if you are too theoretical, you might get lost in the abstraction. But if you have some intuition, regardless of the discipline, it can be business, economics, physics, etc., or engineering, you will understand better the concept. And that is perhaps the reason I decided to present the problem, which is in the book, although it's a physics problem, because I think it will make you understand the concepts better. So, up to this point, we know the velocity. And in order to go from velocity to position, we have to integrate again. Now, the goal is to find the distance. So, ds over dt, so the definition of velocity is the derivative of the position with respect to time, right? And so we know that this is minus 22 times t plus 66. Now, if I want to find the position, I have to integrate the derivative of the position with respect to time, right? I will get an indefinite integral again, and then I will use also part of the info in the problem that I knew in order to solve the problem. So, again, the integral and the derivative are inverse operators, loosely speaking. And then I do the integration over this formula that I have. So, the integral of ds dt, which is minus 22 times t plus 66 times dt. So, let's perform the integration, right? So, have s of t, have minus 22, t squared over 2 plus 66t, and then don't forget your constant of integration, which is a second constant of integration, which is c2. I simplify a little bit, I do the division, I have minus 11 t squared plus 66t plus c2. Okay? Now, we have another initial condition, which is s of 0 equal to 0. And the reason, well, this is telling you that the initial position and the initial time t equal to 0, when we started like basically measuring, is 0. First of all, because s is defined in order as the distance traveled after you apply the brakes. Formally speaking, it's like when you start to care about the distance. So it's like your origin in your frame of reference. So it has a little bit to do with the frame of reference that you choose, but also with the definition of s of t. So it's equivalent. Okay. I'm going to do some comment, doesn't matter too much. So the initial position and the initial time is 0 by definition of s. So what we know is, let's evaluate s of 0 with this function, right? So this term would vanish, this term would vanish, I would only get c2. So once that I know this, I can simply, well, I knew that s of 0 was equal to 0, so this determines completely the constant of integration number 2, so c2 is equal to 0. Now, I go back to the definition that I had, and this determines completely the position, and then my problem is, in terms of knowing the position and the velocity, is mostly solved. So s of t is minus 11 t squared plus 66 t. c2 is equal to 0. Okay? So, now, the question was, basically at which time the car stops. So when the car stops, it has a velocity equal to 0. So by knowing the formula for the velocity, I will find the time when b of t is equal to 0. So rephrasing the final part of the problem, the car stops when the velocity at a given time t to be determined is equal to 0. Now, we know the formula for b of t, which was here, okay? So that implies that at a given time t to be determined, b of t is equal to 0, which is equal to minus 22t plus 66. So I simply have to pass to the other side and divide. So that means that t is equal to 66 over 22, which is equal to 3. So we know the time, that is part of the answer. And the second part is basically in which position does it stop. So we need the time because we want to evaluate in the position function, okay? So the question is, how far has the car traveled up until it stops? I cannot solve that without finding the time in which it stops, which is why I'm using the equation for the velocity. And then once I know this time when it stops, I plug it in the position. So at the time 3 in seconds, I evaluate the position function. And then I have the position at the time 3. Go back to your formula, which was over here, which is minus 11 times 3 squared plus 66 times 3, which is minus 99 plus 198, which is 99 if you do the computation in the units of feet. Most importantly, in this physics problem, you have to integrate twice because basically of the physics laws. Okay, so that we assume some common knowledge from high school, but even though we integrate twice, we have two constants of integration because of this procedure, and we need two pieces of information, which is why for these kinds of problems in physics, when you have basically second derivatives, you need two initial conditions. One for the initial position, which was s of 0 equal to 0. The second is the initial velocity, v of 0 equal to 66, because you will determine two constants, okay? So you have C1 and C2, which are completely determined by the information of the problem, and you're mostly done. But the scope is clear. I have a problem, I'm given the derivative, I have to integrate to get the original function. I need the constant because I have an indefinite integration. The constant will be determined by the extra piece of information, which is either the point through which the function passes, or the value at a given cost, or the velocity and the position at the initial time. That is the summary if you want to take a moral from this story, okay? So try to review these problems. At this point we have done 3. 2 of them quite applied, so I think it gives more intuition about this concept. And as regards of this section, we're finished. So we continue with the section 5.2, which is integration by substitution. So now we will explore some techniques of integration. This one, I'm pretty sure that even in your mind or in one of the previous problems that we have performed, without saying it, we have used it. I'm almost sure, especially with a simple function. So let me describe the technique and then you will see why it makes sense, okay? So, in the new section, 5.2, integration by substitution. It's always good to learn from an example, and then you take away from the example the technique, okay? So the example, in this case, is the integral of the function 3x plus 5 to the 7th power dx. Now, before I even write the method, how would you do this? Maybe you have seen this before. Would it help if instead of basically 3x plus 5 I had x? Would it make the problem easier? What if you had x to the 7th power dx? We already know how to perform that one, right? Because you have x to the 8th power divided by 8. So if that was the problem, it would be easy because we have some rules. We don't have that problem, but we can make a change of variables to make our life easier and get a problem of that sort. So, the idea is to make a change of variables of the form, let's say that you define a function or a quantity u, which is equal to 3x plus 5. Now, the second piece of info is what is the derivative of u with respect to x? You know this by this point. What is it? What is the u over dx? 3, right? Okay. So, look. Well, you take the derivative of u with respect to x, you get 3. So, okay, compute u prime, whatever. There's a reason the notation of integration has this dx. It's not accidental. And again, you will see why I was very insistent on this Leibniz notation of the df over dx, because it makes your life much easier if you understand the intuition behind it. The derivative is the limit of a ratio, right? And so approximately it's basically, well, if you have this interpretation of the tangent line, is the ratio of the change in u when you change x. Now, if I were to write something of the sorts, basically delta u around 3 delta x, you kind of like would give me a pass. Because this is the approximate change if I change x. How much does delta u change? It changes 3 times the change in x. Now, there is a reason this notation is invented, right? And so this is actually valid. It's a little bit like playing with this quotient, but there is a physical reason behind it, which is that the derivative is the limit of a ratio. So of course, it's basically like, let's say, instead of measuring x, you measure u. That is telling you that the limit of that ratio is 3. So approximately, if you measure the pieces of delta x when you go in the x domain and you do this, and then you go to a different space, which is u, the change in u is 3 times the change in x. So this notation is not so crazy. There is a reason behind it, and that's the physics behind it. It's measuring a quotient, and will also help you in the change of variables. So it is not without intuition that we will make this change where du is equal to 3dx. The intuition behind it is pretty much this. I'm being very insistent because we're going to use this kind of change very often. And at this point, you might think that is only notation, but there is a mathematical reason behind it, which is this. Okay? So du is equal to 3dx, and I could pass basically the 3 to the other side, and I have dx equal to 1/3 of du. If you want, it's basically what is the proportion of the change if you go from the variable x to the variable u, because this function is very simple. It's a linear function. There's a factor of 3. So of course, if you change x a given amount, the change in u is going to be 3 times that change, especially for this function, for the computation. If you want exercise, take 2 points, u1 and u2, defined by points x1 and x2, compute the delta u. It will be exactly that. It will be 3 times delta x. For linear functions, this holds. There is no mystery behind it. It will be, when we look for more complicated functions, when this might require some thinking, but it's essentially, bottom line argument is this. So, my point, after having made a big fuss about this, is that I can go back to this integration. And now, I have a variable u, which is to the 7th power, and I know that dx is equal to du over 3. So this is 1/3 of du. I take out the constant of integration, and then I have the integral of u to the 7th power, du, so I have 1/3. And then this one is easy, because this is the same formulas that we saw in the first class. So this is u to the 8th power divided by 8 plus a constant of integration. So the result of that integration would be actually the integral of 3x plus 5 to the 7th power dx u8 over 3 times 8, which is 24, plus a constant of integration. Now, I still have to substitute, because I know that u is equal to 3x plus 5. So this is 3x plus 5 to the 8th power divided by 24, plus a constant of integration. And this is the final result. This is a simple problem, but we can learn a lot from this problem, which is that basically, by making a change of variables, we can make our life much easier. Now, you can verify this computation, because what is the integral? You find an antiderivative. So a function such that if you take the derivative, you get the original thing, right? So if we want to verify the computation, I'm not claiming that at this point perhaps everybody has understood, but at least I want to verify that the computation is correct, and from that we will get to the general idea. So if we want to verify the computation, I would take the derivative with respect to x of this object, 3x plus 5 to the 8th power divided by 24. So you have 8, 3x plus 5 to the 7th power, derivative of this times 3 divided by 24. 8 times 3 is 24. So you have 3x plus 5 to the 7th power. I didn't take the constant because the derivative would be 0. But this is precisely saying that this is the solution to the problem, right? Because the integral is to find a function such that its derivative is the stuff that is inside. That is exactly what I have found, right? I take the derivative of that other object, I recall, or I get back 3x plus 5 to the 7th power. So actually the method worked, okay? So the thing to take away from this is that I can do perhaps a change of variables to reduce the original integral to a much simpler function for which I know the rule of integration, which might be very easy. That is the bottom line of the method. I mean, integration by substitution is clear that we're going to do a change of variables. So we can learn a lot from the simple example, and now after the simple case, we can present the theory in general. That is the way we can learn a lot. So in general, we would consider an integral that can be written as, and so you have your integral, right? Okay. And the way it can be written, this is by assumption. It's a function g of a function u, which is a function of x, so g of u of x, and then you have u prime of x, the derivative of u with respect to x, dx. I don't know how I got it, somebody gave it to me, okay? For certain functions, g and u. Let's say that you're lucky enough that you are in that situation. It's just by assumption, okay? Now, suppose that g, capital G now, it's a different function, but it is an antiderivative of little g. So what you have is that g prime of derivative of capital G is equal to little g. Okay, that's why it's the antiderivative. Now, by the chain rule, if I take the derivative of a function g of u of x, so it's compounded, so you have a composition of functions, you use the chain rule, right? First you have g prime evaluated at the point u of x, and then you have the derivative of the argument, which is u prime of x. Now, by assumption, I know that capital G prime is equal to little g, so I will plug that in. So this is little g evaluated at the point u of x times u prime of x. And now, oh surprise, right? Because, look, this is telling you that this object, you took the derivative, you applied the chain rule, you have this. And actually, this is the argument of the original integral. So if I were to substitute this back here, the problem is much easier because I know that the derivative and the integration are inverse operators. So I would actually get as a result g of u of x, capital G of u of x, plus a constant. So this is the more general version of the little problem that we had before, where the function u is perhaps nonlinear. But we have all the conditions. We have an antiderivative, we have the derivative, which was very simple because it was a constant in the previous case, and we can change the problem to make it look like that. Okay? That's why we jump from the simple case to the more general case. Now, if I were to integrate and both sides of the equation, so let's say that I were to compute the integral of this, right? Integral of g of u of x, u prime of x dx, that is the integral with respect to x of, plug in this object, derivative with respect to x of g of u of x dx. Now, I know the integration and the derivative are inverse operators. So of course this cancels out and I get capital G of u of x plus a constant of integration because the problem is an indefinite integral. So look at this for 1 second, okay? I'm using all the pieces of information. I was lucky enough to have that as the form of the integral. I also know the antiderivative, so I know the big G, such that big G prime is equal to little g. And then I use that piece of information because then by conclusion of the chain rule, basically this piece is very important. Because look at what we're doing, right? We're applying the chain rule, and as the consequence of the chain rule, we have that u prime. So without that u prime in the original problem, yeah, the problem is not as simple, but we're lucky enough to have it. That is why, by assumption, we have that problem. And now, because we have it, we do the substitution over here of that object, which is simple, because you're canceling out the derivative with integration, okay? So you have big G evaluated at u of x plus u. It's the same technique for a much general problem in this case. So the moral of the story is to think of u, which is a function of x, u of x, as a change of variable whose differential, so differential is this delta u thingy. And the differential du satisfies u prime of x dx. So this goes to the fact that, I mean, well, if you want du over dx is equal to u prime of x, this is just a notation, and you play with the quotients with the argument of the ratio that I was telling you, so du is equal to u prime of x dx. The argument is that this would happen approximately when I take the increments, the delta x. In the limit, it's true. Because what you're doing is basically change of variables. So you go from the space of x to the space of u. And this delta u is basically taking track of how much the impact of a change in x has an impact in the change in u. That's why you need that factor u prime, which was 1/3 or 3, well, I can't remember. But in the previous problem, you had like this 3 difference factor. But now you will use it. And in the conclusion, what you would have is again that the integral of g of a function u of x, u prime of x dx is equal to the integral of g of u du, precisely because of this differential, which is g of u plus a constant, and then you substitute g of u of x plus a constant. If it's the first time you see this, it might not be so simple. I think the fact that we started with a linear example, it's very helpful because for linear functions, basically take 2 points. I mean, if you have this function u of x equal to 3x plus 5, consider if you take 2 different points and then you consider delta x, the difference between those, do the computation on what is delta u. And there you get it exactly. It's just a difference, right? You have u1, 3x1 plus 5. u2 equal to 3x2 plus 5. Take the difference u2 minus u1. So you have 3x2 minus x1. The constant has vanished. By definition, delta u is u2 minus u1. So you have delta u equal to 3 times the difference, which is x2 minus x1, which is delta x. So for linear functions, it follows perfect. Okay? It is when you have more complicated functions, which are considered in this case, that the situation might get more complicated. But okay, we have presented the theory, and we will just give some guidelines in order to follow this method. So, integration by substitution method, step by step, for the integral of f of x dx. Right? So step 1 is to choose a substitution u equal to u of x. That simplifies the integrand f of x. So, which is the first thing that we did in a simple example, right? So you have to find some function that might make the problem simpler. Then the second part is to express the entire integrand in terms of u and du, which is equal to u prime of x dx. This is telling you to change all the variables. I mean, you cannot, if you do the substitution up to a point where you still have functions of x, like in the previous problem, let's say that you change the 3x plus 5 to the 7th power to u to the 7th power, but you don't change the dx. You cannot proceed, because you either have the variables in u or in x, if you're going to do the substitution. That's clear. So the third part is that now the integral should have the form, you have changed the variables from x to u, so now it will look like something of the form, let's say, u of u du. Yeah, and then you have the, yeah, that's why you had the u prime dx. And then, well, find antiderivative, capital G of u for u of u. So basically, you would have, okay, this u prime, u equal to G of u. So you plug it in and you recover. And then the fourth part is to replace simply u by u of x in G du, u of u, to obtain the antiderivative G of u of x for f of x. Okay, and then in that case, what you would have f of x dx equal to G of u of x plus a constancy. So, the last piece of info is how to find a suitable change of variables for the substitution. So the first one is, if possible, choose u so that u prime of x is part of the integrand. The second is to consider choosing u as the part of the integrand that makes f of x difficult to integrate directly. The third is to don't over substitute. So basically, in the example that we had before, is to do not use u equal to 3x plus 5. So basically, making this the actual u would be the bad choice. The thing inside would be a good u. With the 7th power, it doesn't make any sense in the previous example. And the fourth is to simply persevere in the sense that you might not be able to do it at the first time, so you might need 2 substitutions, but with 2 you might be able to get to the problem. So this is a good time to stop. We will start with some examples in next class.